Okay, people, back at it. Section 4, Chapter 6, Section 4, Logarithmic Functions. So we got a little taste in Section 3 about what logs are all about and how they're related to exponentials. And now we're going to dive a little bit deeper into really focusing more on logs, what their graphs look like, how we can use them to solve equations and situations, really. We're going to introduce them as just one more operation that we're comfortable using. Okay, so example 1, we're going to identify some key features of a graph of a log. So we are asked to graph the function y equals log base 2 of x. But if you're like me, I have really no idea what that means. I don't know how to take the log base 2 of many numbers. Well, maybe, but we're not at that point yet. But what we are at is we can think really well in terms of exponentials. So we know that the inverse of this log function is an exponential of the same base. So in this case, take the same base of 2 and make it the exponential 2 to the x. So now this is something we can create a table out of because we're really good at thinking in terms of repeated multiplication. That's something that we're really savvy at doing. So let's do our standard 5, -2, -1, 0, 1, 2. So plug in 2 to the -2, flip it, becomes 1 over 2 to this 2 squared, so 1 over 4, so 0.25. Plug in -1, becomes 1 over 2, which is 1/2. Plug in 0, anything to the 0 is 1. Plug in 1, 2 to the first power is 2. Plug in 2, 2 squared is 4. So now we know that the inverse means we flip our x and y. So it makes the table of log base 2 of x really, really simple to create. So we just flip 0.25, -2, 0.5, -1, 1, 0, 2, 1, and 4, 2. So a lot of times, thinking about things in terms of exponentials can really help us create a table because it's super easy. Then you just flip them. So let's see what that actually looks like on a graph here. Okay, so I'm just going to draw a little mock-up of a graph here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we want to graph log base 2 of x. All right, so let's do it. Let me use a different color. So what we want to do is we want to graph because we want to think about, well, what are the general features of logs? So we go to 0.25, -2, 0.5, -1, 1, 0, 2, 1, and 4, 2. And you can really see this arc, this curve start to take shape. So in a lot of ways, in this section right here, it might kind of resemble a square root function. It's not, but we can kind of just get general shape. It's got a curve. We can hopefully see that there's some asymptote that's occurring right here. It's coming really, really close to that point, but it's not touching. Okay, so let's talk about a couple things here. Let's talk about domain. Well, where do we see, are there any limitations on our x values? Well, we don't see any x values over here in the negatives, and it looks like they're coming really, really close, but they're not touching 0. So our domain is then all x values that are greater than 0, because as we go over to the right, we have an arrow, keeps going, keeps going. Let's talk about our range. Well, this arrow is going to go on forever. We have all the range values over here, and this is gradually going up and up. So we have all the range values in the positive direction. So our range then is all real numbers. Can we identify an intercept? Absolutely. It's right here at the point 1, 0. Do we see an asymptote? We definitely should, because we're going to start approaching these really, really small x values. Are going to run down, 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 but they're never going to actually touch 0. So our asymptote is the vertical line x equals 0, also known as the y-axis. And then lastly, let's just talk a little bit about, well, what are we seeing at the ends? What's the end behavior? So as x approaches to the left, to the left, to the left, it's not going negative. We know it's only going to 0. And what's happening to our graph? Well, our arrow is pointing down towards negative infinity. And as we look to the right, to the right, to the right, to the right, looks like it's going on forever. So as it approaches positive infinity, y is gradually increasing as well and getting up towards positive infinity. Okay, now what I really want to show you guys is I really want to show you how that compares to the exponential. So again, we can look at a graph and we can say the domain, say the range, say the intercept, say all this, but what really makes it stick is that it's the exact inverse of the exponential. So watch. So I'm going to graph the exponential. -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. And we see our classic exponential curve take shape. So we know that they're inverses because we look at them and look, they're symmetrical over the line y equals x. They're these two curves that start really, really close to each axis, bend in towards each other, and then flare out in opposite directions. And guys, here's the thing. I'm going to denote all of these things. So look, this asymptote was at y equals 0, and what do you know? Our asymptote for the inverse is at x equals 0. This exponential had a intercept at 0, 1, and guess what? Our log, which is the inverse, has an intercept at 1, 0. We flip-flopped it. This domain is all real numbers. Well, since we flip x and y values, our range for our inverse log is all real numbers. This range was limited to only y is greater than 0. Sure enough, we flip-flop, our y's become our x's. This log's domain is now x is greater than 0. And you can see the same patterns continue. So it's really just a matter of if you are confident knowing about exponentials and being able to see what the graph would look like and know that it's this certain shape with an asymptote at the x-axis with an intercept at 0, 1, we can just flip that idea to get a real good picture of what a log of the same base is going to look like. So this is a really good idea how we can actually see the key features of a logarithm to any base. There'll be slight changes, but any general log of some base is going to look pretty much like what this graph is here.